Okay, so in this problem we have a spring here. So this is like a wall or something, and the spring is attached to the wall. And on this side, the spring is attached to a box. Let's just say some sort of block, and this block has a mass of 2.5 kilograms. And this block is pushing in on this spring by 0.03 meters. So this spring is not in its natural state. It's pushed in about that far from its natural state. This spring's spring constant K is 840 Newton meters. That's actually Newton meters. Great. And then what else do we have? So this is the mass. This is how much is compressed. This is the spring constant. This is the block here. This is the floor that it's on. This floor does have some some friction on it, and so the friction coefficient, kinetic coefficient of friction is 0.4, and the block is initially at rest, which means there is no velocity. So what we're going to do is we're going to release this block from rest, right? We're going to let it go, and it's going to spring because it's compressed this way. It has potential energy, right? And so it's going to spring. It's going to go in this direction. And what we want to know is what's the speed of the block when it has moved 0.02 meters. So it's compressed in 0.03. Well, what's its speed or velocity once it's reached once this thing has moved 0.02 meters? Now, it's still compressed. After you've moved this thing this way, 0.02 meters, it's still compressed by 0.1 because it's currently compressed 0.03. That's how much it's compressed. And we're going to move 0.2, so 0.02. So that leaves us with 0.01. So after it's done its movement, the spring is still in its compressed state. It's just less compressed, okay? All right, so that's set up, and what we want to know is how fast is this thing going? Because it's initially at rest, no velocity. How fast is it going? All right, so let's do this. So what I'd like to do is do this by showing a diagram. Let's do force versus displacement. So this is force, which is in newtons, and this is displacement in x, and we'll call this is in units of meters. And this is what I'm showing here is force versus displacement of the spring. Okay. So the spring constant, which it gave, was 840 Newton meters. So basically, it's this linear line right here. And so an ideal spring starts at 0, so its origin starts at 0, so it doesn't have a y-intercept. Well, the y-intercept is 0. And so this force, as a function of x or displacement, and x means, what does x mean? It means how far from its non-stretched or non-compressed, like its natural state. So if it's pushed in, say 1, then that x is -1. So sorry, let's say it's pushed in 1 meter. I mean obviously it would have to be a big spring, but or a half meter, whatever. So if it's pushed in 1 unit, 1 meter, then that's x. Or if it's stretched 1 meter, then it's positive x. So when it says x here, it means x from its normal. So the origin is where it is normally. Okay, all right. So let's go back to this. And yeah, so f of x, which is the force as a function of x, is equal to 840, and of course it's Newton meters. Now this is a function in x, so there's x there. So what that means is when this spring is stretched or compressed, you could do it either way. Let's say by 1 unit or 1 meter, it would be 1 times that. 840, and that gives you your force, new force. That's the force at 1, for example, 1 meter. So if this were 1 meter, you would say 1 which is x. 1 times 840, which is 840. If it's 2, that's the next is 2. 2 times 840. So then that's your force. Okay? All right, so we have this function here, and there's no y-intercept. You could say plus 0 if you wanted to, just to be pedantic about it, just to show that there is no y-intercept in this ideal spring. All right, so but the interesting thing about this graph is that the area under the curve represents energy or work. Okay, well, of course, work and energy are like opposites of each other. Energy is like, something has, like an object has some amount of energy, and then work remember what work does. Work just changes energy, right? If there is no work, then energy doesn't change. So that's the point of work, is to change energy, like move it around. If there was no work, then the universe would just be static. Okay, so it says that we're compressed in initially 0.03 meters, but we're going to let this thing move 0.02. Okay, so if we do that, then it'll go down to 0.01 meters. So let me just show that again. So it's initially compressed this much, and we're going to let this block go this way. So that means we're going to release it. So it goes down. So it's only compressed 0.01. So we remember 0.03 minus 0.02 equals 0.01. So we're going to go from this amount of compression of the spring to this amount of compression of the spring. Okay? So the spring is a storage of energy, right? It's potential energy that it's storing in here. So what we're going to do here is, so this whole thing is potential energy, right? This whole thing is potential energy that's getting released. So once we move from 0.03 to 0.01, we're going to release that potential energy. But how much is it? Well, you can see here, this is just the area. This is the curve, and I'm going from this to this. So this is just some calculus, right? Some an integral. So then I can just write that formula, right? I can say, well, I want to find the integral from 0.01 to 0.03 of the function. What's the function? 840 x, and this is with respect to x, so it's dx. So I want to do that integral, right? And so that integral is this area under the curve. And if you do that, you'll get 0.0336. And because it's under the curve, the area under the curve is in joules, right? Joules. So this is 0.336 joules. So when the block moves from 0.03 meters to 0.01 meters, it has released 0.336 joules of potential energy. Okay, so now this energy has been released. What's going to happen to it? So it's no longer potential energy, right? Potential energy is now gone. It did have potential energy, and now, well, there is leftover potential energy because this, let's do it like here, this right here. This is still potential energy, right? So right here. This is still potential energy right here. Because we haven't actually, it's still stored. The spring is still compressed 0.01. So we didn't release all of it. We just kind of released part of it, right? Think of this like a battery, right? Where there's a battery here, and we use this much of the battery, but this much, but then this battery right here, this part of the battery we kind of left it alone. Okay, so we're only going to use part of the battery, which is energy storage. So the question is, this much energy from the spring that we used, what happened to it? Well, two things happened to it. One, this thing is going to move, right? Now, if this surface here were frictionless, when it moved, there would be no friction, and so therefore nothing would hold it back. And so all of the energy, this potential energy of this 0.336 joules, would be converted into kinetic energy. right? So basically, then this is now kinetic energy, 0.336. But the problem with that is that in this case here, and in real life, there is actually friction between these two surfaces. So the friction is going to eat into that budget, right? You can think of this as like a budget, and I'm going to use a certain amount of the budget for friction, and then the remainder will be for kinetic energy. Okay. All right. So the question is how much energy did friction use? All right. In order to do that, we need to make a free body diagram. So let's do that. So I'm going to do, this is the block right here. This dot represents the block. And on the bottom, of course, is mass times gravity. And on the top is my normal force. Mass times gravity is, the mass is 2.5 kilograms. Gravity, of course, 9.8 meters per second. You do the math on that, and you get 24.5 newtons. And then the normal force is also, because there's only one thing going down, so meaning the vector, so mg is pointing down. So remember Newton's first law, which says the sum, in this case here, the sum of the forces, and we're talking about y, is equal to 0. Because why? There's no acceleration. Remember F equals ma, where there's acceleration. Yeah, but there is no, meaning that if the forces are imbalanced, then there's an acceleration. Here the forces are balanced, right? Because this block is not moving up or down. So the forces are balanced. That means that the normal force has to be the same as the weight, which is 24.5. But one's pointing up, which is positive. So the normal is actually positive 24.5, and then the weight is actually negative 24.5. And you put that together, and you get 0. So the sum of the forces is 0, right? So now we know that the normal force is that. Now this thing is going to be accelerating in this direction, right? So there's going to be acceleration in this direction, right? It's going to be accelerating in this direction here. To the right. Now, because of that, then there's going to be a frictional force to the left, right? There's going to be a frictional force to the left. And the frictional force, you may remember, it's kinetic friction, is equal to mu sub k times the normal force. Mu sub k is 0.4. The normal force, which we just computed, 24.5. You do all the math on that, and you'll end up with 9.8 newtons. You're like, is that gravity? No, in this case here, it's actually 9.8 newtons. That is the force of this friction. Okay, so this friction is moving parallel to the friction. Remember when you do friction times displacement is work. So because friction is moving parallel to this block, you can just multiply them together, right? You can just multiply them. Also, what you could do is this. You could say, oh, okay, you could create your force. Once again, you could create a force versus displacement here. And my force is what? Well, this is my frictional force, which is 9.8. 9.8 newtons, of course. But does this force change depending on my displacement? No, it doesn't change at all. Now, how much did the block displace? Well, it displaced 0.02. That's how much it moved, right? 0.02 meters. Okay? Now, remember the area under the curve, of course, is work. And so, yeah, so if you do 9.8 times 0.02, you get 0.196 joules. So this is how much energy was consumed by friction, okay? Was consumed by friction, okay? All right, so let's kind of put some of this stuff together. We did have some potential energy of what? 0.336 joules. But then we had to subtract. But then that got converted into other energy. Okay, what did it get converted into? Well, first of all, we have to subtract the energy that friction used. So we have to subtract. We'll call this energy due to friction, EF, energy due to friction, and that was 0. We just did that 196 joules. We subtract that. And if you do that, you'll end up with 0.140 joules, 0.140. And that energy, what's going to happen with that? Well, then that's going to become kinetic energy, right? That's going to become kinetic energy. Okay, and then once you know what the kinetic energy is, then you can find the velocity. Remember, so it's 0.140. That's my kinetic energy is equal to 1/2 mv squared. You can multiply both sides by 2 if you wanted to. Get rid of this half, and then divide by mass. Right, your mass is 2.5, and then you can get rid of this square by taking the square root. Okay, and then you end up with your velocity equals 0.334334 meters per second, and that's it, right there. That's your velocity. Okay, so what just happened? Okay, so I'm just gonna write like a think of this like a battery. I had this much potential energy initially in the battery. In this case here, it's the spring. But then I used this much. This much was left over. Over here on the left-hand side was left over. So we'll maybe make that this much was left over. Okay. And then this much here, let's look at my numbers. So 196, 140. So actually most of it was used up for friction. So we could say like this much here. Sorry. This much here was friction. That was friction. And then this much here turned into kinetic. So once everything is done, so initially it was all potential energy, right? Initially it was all potential, but then work happened, and now only this is potential energy. This happened. This was the energy due to friction, and then this became kinetic energy. So while the whole thing was potential energy initially, let me just erase that. If this thing does erase, good job. Okay. So let me just draw it like this. So initially the whole thing was like this. Like this. The whole thing was potential energy, but then work happened, right? Work happened. And then work changed it. So now we went from potential energy, all this potential energy, to just a little bit of potential energy. Some got transformed into frictional energy, right? Basically the particles between the like the atoms and the molecules between the surfaces, they started heating up, right? They got hot, and so that's what happened here. They got hot. Their internal energy increased, and then we had an increase in kinetic energy. So this turned into this, and this because work happened. Okay? All right, that's it.